Hello, ladies and gentlemen. It's me again. We're going to continue with Chapter 7, Chapter 7, Section 7.2, which are trigonometric integrals. Last time we integrated powers of sines and cosines in some special cases. We have to finish off that case, and then we'll talk about secants and tangents. So let's get started with that. Okay, so section 7.2, let's remind us that we're in the case of the integral of powers of sine of x times another power of cosine of x dx. And we handled already last time the case m and n, both either m or n is odd. So let me correct what I just wrote. Either m or n is odd, an odd integer. Okay, now we're going to consider the remaining case. M and n both are even. In order to handle that case, it is necessary for us to apply the double angle identities, which you should have encountered before, but I'll remind you what they say. They say that the square of the sine function of an angle A is 1 minus cosine of 2a over 2, and the cosine squared of A is likewise 1 plus cosine 2a over 2. So these identities are extremely useful, and as we'll see in a moment, so let's consider an example. The integral of the square of the sine function of x dx. Let's see how we can do that. Now the idea is to simply apply this identity here to replace sine squared x with the thing on the right-hand side. Okay, so we do that and we get, I'm going to stick in 1 minus cosine of 2x over 2 dx. And I'm going to break that up as 1/2 the integral of dx minus 1/2 the integral of cosine of 2x dx. Okay, now the first integration is going to give me an x over 2. And the second one, you could either do it by substitution or you can guess at the answer. The idea is the antiderivative of cosine of 2x should be something involving sine 2x multiplied by a fudge factor. So we just have to figure out what the fudge factor is. So let me put here sine of 2x. Now the derivative of sine of 2x is 2 cosine 2x, but we want 1/2 cosine 2x to be the derivative. So we have to fudge it by 1/4. So if we take the derivative of sine 2x multiplied by 1/4, you'll get 2/4 sine 2x, which gives me 2/4 cosine 2x, which gives me 1/2 cosine 2x. And then we have to add a c at the end of all of this, and that's the answer. So this was pretty simple. This was not hard at all. Okay, so let me save this whiteboard. Okay, let's do another example. That will be the integral of sine squared x cosine squared x dx. So both powers, this is the case m equals 2 equals n. And we appeal to the trig identities. So sine squared x is 1 minus cosine 2x over 2. And that's multiplied by cosine squared x, which is 1 plus cosine 2x over 2. And then we get a dx. And now we can bring out the constant. That's 1/4. And what's left over is 1 minus cosine 2x times 1 plus cosine 2x dx, which we can C as just the same thing as 1 minus cosine squared of 2x dx, which is 1/4 of the integral of sine squared 2x dx using the Pythagorean trig identity sine squared plus cosine squared of an angle is 1. Okay, so now how are we going to do this? Well, I'm going to just do a simple u substitution, u equals 2x. And to get what? To obtain then du is 2 dx. And so we get this integral is 1/4 the times, so we don't have 2 dx, we only have dx, so we get 1/2 du is dx. So it's 1/4 times 1/2 the integral of sine squared of u du. And by the last problem, so we have an eighth coming out, and the last problem says that this is 1/8 u over 2 plus sine 2u over 4, and then we'll add the c on the outside. And this is when we expand 1/16 times u is 2x, so it's 2x plus sine of 4x over 4 plus c. And if we will, if you allow me, I will make this 2/16 into a 1/8 to make it simpler. So it's 1/8 x plus sine 4x over 4 plus c. So there you go. And oops, I see a mistake in what I claimed. It's not a plus sign. If you look back at the previous problem, there's a minus sign here. So it's going to be minus. And that should do the job. Okay, so let me save this screen. And let's move on to the next problem. Okay, so now we're going to consider the case of integrals involving secants and tangents. So this is going to be part 2, and it'll be integrals of the type secant, a tangent to the m of x times secant to the n of x dx. And in this case, we're going to appeal to the trig identity secant squared x minus tangent squared x equals 1. So this allows us to write, for example, tangent squared x minus is equal to secant squared x minus 1, and likewise it allows us to write secant squared x as tangent squared x plus 1. So these are the forms of the identity we want to use. Okay, so so there are, as before, several cases to consider. This is a harder set of integrals to do in general. As you'll see, there are more cases to consider. So let's consider the case 1, where n is even. So how do we deal with that? Okay, so the idea when n is even is you go to the factor where n is even, that's the secant to x to the power of n, and I'm going to require n to be bigger than 0 here. So in this case, so we'll break off secant squared of x and express everything else in terms of tangent x. So let's do an example to explain what I mean. So here's an example. The integral of secant of x to the power of 4. Okay, so what do? According to this recipe, we break off a power of secant squared, So secant to the fourth times secant is secant squared times secant squared x dx. We group this term secant squared x dx together as one unit, and then the remaining stuff we turn into tangent. So this is secant squared x is tangent squared x plus 1. So and then so we get tangent squared x plus 1 times secant squared x dx. And then you have to remember that the derivative of the tangent function is secant squared. So let's let u be tangent x, and then du is secant squared x dx. And that we have a secant squared x dx. So this becomes the integral of u squared, oops, plus 1 times du, which is u cubed over 3 plus u plus c. And then we convert back to tangent x because u is tangent x, tan cubed x over 3 plus tangent x plus c. Voila. So that is an example. So that's the case when the power of the secant is even. And then we move to the next case. Let me save the screen and then clear it. Okay, so let's do case 2. Will be the case where m is odd. Okay, so in that case, if m is odd, you break off a factor of secant x times tangent x and use the identity after that. So let's see what I mean by that. Let's do an example. So here's the integral, and here I'm assuming n is greater than 0 for this to work. So let's consider the case where we look at tangent cubed of x times secant x dx. So this is the case where m is 3 and n is 1, and that fits this case. Okay, so we're supposed to break off a secant x times tangent x. So this becomes tangent squared of x times secant x tangent x dx, and the secant x tangent x dx is a single unit we're counting it as. And now we convert the tangent squared to secant squared minus 1. So this is secant squared x minus 1 times secant x tangent x dx. And now we let u be secant of x, and then du is secant x tangent x. And then we get this integral becomes the integral of u squared minus 1 du. Okay, so this then the antiderivative is u cubed over 3 minus u, and then we add a c, and this is secant cubed x over 3 minus secant x plus c, and we've done it. Okay, so that works. That's great, and I'm going to save the screen and clear it. Okay, so now there are a couple of isolated cases to deal with that so I'll call this case 3, where we just consider the integral of tangent x. That cannot be solved using the previous recipe. So this is the case where m is 1 and n is 0. So this is actually very easy to do. This is, you express tangent of x as sine x over cosine of x. And then you're going to let u equal cosine of x, and then du is negative sine x dx. We don't have a sine x dx in the integral. We have a minus. We don't have a minus sine x. We have a sine x. So it's minus du is sine x dx. That's the better way to write it. And then this becomes the integral of minus du over u, which is minus the integral of du over u, which is minus ln absolute value of u plus c, which is minus ln absolute value of cosine x plus c. But from time immemorial, most textbooks do the following. minus ln of something is ln of the reciprocal. So we can think of this as ln absolute value of 1 over cosine x plus c. That absorbs the minus sign into the ln, and that's the same as ln absolute value of secant x plus c. This is an integral that's good to remember. Okay, so that's the integral of tangent x dx. It's ln absolute value of secant x plus c. Okay, let me move on to the next case, which is, again, an atypical case. It's not a general thing. It's just a single integral. So let's consider case 4. It's the integral of secant x dx. So this is the case where m is 0 and n is 1. Okay, so we're going to use a trick in this one. This is something that is kind of, no one knows. This is like pulling a rabbit out of a hat. So you're going to consider secant x. And what we're going to do to secant x is we're going to multiply it by 1 in a very funny way. So I'm going to multiply it by secant x plus tangent x over secant x plus tangent x. And now if we distribute the secant x through the numerator, we get secant squared x plus secant x tangent x and over secant x plus tangent x. Okay, so therefore the integral of secant x, I'll write it on the top, is the integral of secant squared x plus secant x tangent x over secant x plus tangent x, and this is dx. Now, whoever discovered this trick was a magician. I don't know where this trick came from, but it works. So let's let u equal secant of x plus tangent x. So that's the denominator that appears in the fraction of the integrand. And then what's du? That's a derivative of secant x, which is secant x tangent x, plus the derivative of tangent x, which is secant squared of x, and this is all dx multiplied by dx. And that is the numerator of the integrand. So that appears in the numerator. Here's the numerator. So this is like u is on the bottom, and then we have du on the top. So this is just the same thing. I can bring it down as the integral of du over u, which we know to be ln absolute value of u plus c. And that is the same thing as ln of secant x plus tangent x plus c. And there's another integral that you may want to memorize. It's actually it's a pretty standard one that comes up all the time, and it helps if you can remember it. If you can't remember it, no big deal, because this is an asynchronous course with open book exams, so you can just write it down on a sheet. And if you use the same integral over and over and over again, you eventually remember it anyway. So it's no big deal if you don't remember it. You'll eventually know it. Okay, so I'm going to move on to the next problem, which will be the last problem for today. And this is a little lengthier than the others, but so this is like another case. So I'm going to consider this as case 4. So this is the integral of secant cubed of x dx. And this is done in a completely different way than all the other examples. So we're going to let, this is the case m is 0 and n is 3. Okay, so this is just one of those special cases that can't be done any other way. You're going to integrate by parts by writing this as the integral of secant x times secant squared x dx. So this will be your dv, and this will be your u. So u is secant of x, du is secant x tangent x dx, and dv is secant squared x dx, so v is tangent x. And so our integral becomes, I'll write it over here, u times v, which is secant x tangent x, minus the integral of v times du, which is secant x tangent squared x dx. Okay. Okay, so now let me rewrite this by coming down over here to make it a little more legible. So what I'm going to do is replace the tangent squared x by the trig identity, which says that tangent squared of x is secant squared x minus 1. So this is the effect of doing that. And then I'm going to expand. So this is the integral of, this becomes secant x tangent x minus the integral. If I expand, the first term becomes the integral of secant cubed of x dx. I'm breaking up the integral into two parts, and then minus minus is plus, and you get an integral of secant x dx. Okay. So now, what have we shown? We've shown the integral of secant cubed x is given by this three-term expression on the right. So if I bring the middle term that appears here over to the left side of the equation, which is here, what do we get? We get that twice the integral of secant cubed x dx coincides with secant x tangent x plus the integral of secant x, which we did in the previous example as the ln absolute value of secant x plus tangent x. I'll add the c later, so let's call the constant we're adding c prime for now, because I'm going to divide by 2. So if we divide by 2, we get the integral of secant cubed x dx is 1/2 secant x tangent x plus 1/2 ln absolute value secant x plus tangent x plus c, where c is c prime over 2. This is the final answer that you're going to get. Okay, so I think we've had enough for today. This was jam-packed with examples. Next time I'm going to finish off this section. This section takes like 2.5 lectures to cover. So that's it for today. We've covered most of section 7.2, but not all. So have a good day.